So, good morning, and well, first of all, thanks to Carla and Andrew for inviting me to this very nice workshop, online workshop. Okay, so today I will I will try to contribute by discussing quantum interferences in atomic harmonic spectroscopy. Let me have the pointer here. Okay. So, this is an outline of what I'm going to talk about. I will give a very short introduction to harmonic spectroscopy. I think probably all of you are familiar with this, but I will just revise a few concepts. Then I will show you, the system we were interested in study, which is xenon, and in particular the giant resonance xenon, and some results that we got by applying two-color harmonic spectroscopy in this system with our experimental results and the interpretation, or at least the struggle we are having in interpreting these results. So let's start with a very introductive three-step model for the harmonics. As you all know about the process, we have the external laser field that can detach an electron from the valence shell of the atom by tunnel ionization in the first step. Then we have the propagation of the free electron, which is accelerated by the laser field, and then we may have the recombination and the energy, the kinetic energy of the electron is released through the emission of an XUV photon. And this can beautifully be let's say, depicted in a quantum model, which is the Lewenstein model, that relies on two main approximations, which is the strong field approximation and the single active electron. So we basically ionize only from the outermost valence shell because of the tunnel ionization probability. And then we can write our harmonic spectrum as an integral of this expression, in which we can really recognize the ionization step, the recombination step, and the propagation, which is associated with these phase gained during the propagation by the electron. And I mean, for the dipole matrix element, one can use the hydrogen-like atomic dipoles, as here. And so then next step could be to basically relate these integral to electron trajectories in a simple way with saddle point approximation. What one can do is basically consider all the points which are basically ionization time, recombination time, and photon energy that are coupled, in which this phase, the derivative of this phase is zero. And so we can write the spectrum as a sum of trajectories. And this is very nice because it's really related to the very simple three-step model. And it can give insight in the in a lot of experiments done in harmonic spectroscopy. Basically, what happened is that you can do an attosecond experiment just by collecting your harmonic spectrum. And this is because there is a natural mapping between the electron recollision energy, so this is an harmonic spectrum, and each electron recollision energy corresponds to a specific trajectory, and so a specific ionization time and recombination time. And so this mapping is basically so you have the attosecond nature of the process that is mapped in the harmonic spectrum. And so how does this is affected by quantum interference in harmonics? Well, basically what happens is that in ionization, you may have different paths that are initiated during the ionization step. And then you can have recombination with a system that has many electrons that are maybe rearranging, and this electron can scatter with the recombining electron can scatter with the electron in the ion. So somehow you can have interference also in the recombination step. And the point with harmonic spectroscopy is that all these possible phenomena are inside the harmonic spectrum. So it's a kind of an easy way to collect the information experimentally, because you just have to collect the spectral intensity. But then you need a way to disentangle this information from the spectrum. And how this can be done? Well, a relatively easy way is to manipulate the electron trajectories. This is our clock. So the time between ionization and recombination corresponds to a trajectory and to a specific photon energy. And like you can achieve basically the control of the electron trajectories. This allow you to control basically the pump probe delay in your experiment. And how can you do that? Basically by tailoring the external electric field, which is driving the electron in the propagation process. This can be done in different ways, but one way, which has been, quite effective, is to add a second color to your fundamental driving field. Here is a sketch of how this driving field looks like. You have the second color, and then you can change basically the delay between these two components, so the phase between the two colors. And what happens is that the second color displaces the electron away from the parent ion, and it can basically make the electron recombine or not, depending on the kick that the second harmonic is giving to the electron and the change in the electron trajectory. So this is a small movie in which you can see trajectories in this two-color field. For the electron, the blue dot is the parent ion, and then like when you see a colored trajectory, this leads to recombination, and it's a different color because it's a different photon energy emitted for each of these trajectories, corresponding to a different phase delay of the second color component. So basically what happens is that you have the second color that acts as a gate that selects a specific trajectory with a given energy. And there is an optimal phase delay between the two colors that maximizes the probability of recombination for each of the photon energy, of the harmonic photon energy. So this phase as a function of the photon energy is a measure of the time between the ionization and recombination time, and it's your clock to probe the dynamics. Here you can see a calculated experiment in which you see like this is the photon energy of the harmonic spectra, and here you have basically the phase that optimize each photon energy. Here you can see basically that it goes like this. This is a specific calculation, and here you have like that basically your phase increases up to the cutoff, and then it goes down beyond the cutoff. Okay, and so well in the lab this is a relatively easy experiment, and what we have done is that we used a driving laser which is an OPA at 1.5 micron with 20 femtosecond pulse duration and 1 millijoule energy, and we did a simple setup for basically adding a second color with perpendicular polarization. And well, we retimed the two color in order to be overlapped in time, and then we have a pair of few silica wedges that can change the phase easily of the two color. And then we generate harmonics as usually by focusing this two color laser field on the gas jet with a pulse bulb, and then we acquire the harmonics with a flat field spectrometer. And yeah, well, basically we were helped in setting this up, and we established a very fruitful and long collaboration for doing two-color harmonic spectroscopy in our lab with a group of Thierry Tudovic, and in particular also with Ada Seufer and Barry Brunner. And they, well, we did several experiments together, but this is one of them, basically. So these techniques, it's a promising approach that has been established many years ago by Merit, I think still when she was in Canada. And here I just show three examples. One is very recent of the application of this technique in order to study, for example, ionization and recombination times, or different pathways initiated during the ionization. And then you have, like, for example, here, these interferences that you can see, and you can see structure and spectral phases in the experiment. So this is just like some state of the art. So what we did, it was that we decided to study xenon. In the next slide, I will explain you how we developed this idea, but basically, like, xenon is, it's very nice to work with in the lab because it has a very high harmonic yield. It can be modeled quite easily, or at least this was what we thought before doing the interpretation of this experiment. And it shows electronic coloration because, of course, it's a big atom. And in particular, what happened is that there is this phenomenon known as giant resonance around 100 eV. And well, it works like that. Like you can have ionization from the 5p orbital of the xenon. And then when you have the recombination step for generating the harmonics, you basically have two channels. You have a first channel in which the returning electron recombines directly with the 5p electron vacancy. That is this part here. And then you have a second channel in which the returning electron promotes an electron from the 4d inner shell to the 5b valence shell, and then the recombining electron recombines with the 4d electron vacancy. And so these two interfere constructively and give rise to this giant resonance, which is very well known also in photoionization and the synchrotron with photons of 100 eV energy. And well, what happened it was that we, in end of 2013, we read this paper from Stefan Pabst and Robin Santra, in which they were reproducing, like basically what they were doing, it was to model the harmonic spectrum in xenon and looking at the role of the giant resonance, so of the inelastic scattering happening in the recombination process. And what they find out is that they could switch on and off the different channel, and so switching on and off the multi-electron effects. And they were able to identify the contribution of this scattering in the final spectrum. So we contacted Stefan and we said, okay, this would be nice if we can try to use two-color iodine harmonic spectroscopy to measure this recombination time, so this time of the electron scattering during the recombination. So we performed the experiment. This is an experimental result from 2014 that Davide Facciola performed in our lab. So basically what you see here is that this is the harmonic spectrum, this is the photon energy, this is a sequence of harmonic spectrum acquired for different phases between the two colors. You can see like the periodicity here. And then we started, let's say, the interpretation of these results. Like we can look at one of the period here, and you can see the behavior. Well, basically what you can do is that you can retrieve the experimental phase that maximize its photon energy with Fourier analysis, and you get the black curve here. It's quite noisy where you don't have a lot of photons, but I mean, like you can see the behavior, the black line behavior here, which is quite clear. And then the first thing that Davide did was to calculate basically the theoretical phase that you would expect with strong field approximation, single active electron, and saddle point. And the point is that basically, and this is the blue curve, this blue curve is overlapped to the black curve only if you have a cutoff at 71 eV. So this was the first thing that was struggling us back in 2014, that we were somehow able to see trajectories beyond the cutoff. We have a huge signal beyond the cutoff. And it took us a long time to believe this signal and give an interpretation to this. But in the end, basically, like now we trust, also because of different experiments, that we have this cutoff at 71 eV. There is a clear change of the slope of the phase at this energy value. And so we can see trajectories beyond the cutoff. And this was already a nice result. But then we have a discrepancy between the black and the blue curve, which, I mean, we thought, okay, this may be due to the fact that the blue curve is single active electron. We are dealing with the multi-electron effect. So maybe that this discrepancy is hiding the information about the recombination time and the scattering time we are looking for. And so what we tried to do at first was to kind of adapt the strong field approximation, the single active electron strong field approximation, in order to, let's say, take into account multi-electron effect. And how can we do that? Well, we basically adapt the perturbative approach proposed by Dror Shafir in the group of Neri Tudojevic in 2012, that does not consider the phase associated to the propagation along the perpendicular direction, along the second harmonic field direction. And then we also use a complex dipole calculated with a random phase approximation instead of the hydrogen-like dipoles for the saddle point calculation. So we change our saddle point equations to this one. And then what happened is that around the resonance, you get new recombination time that differ by only 20 attoseconds with respect to the original one. So we thought, okay, this is actually the right timing for this recombination process that we would expect. So maybe we are really sensitive to this very tiny delay introduced by the multi-electron process. But unfortunately, this was really an unlikely coincidence. Okay, first, I show you here. So this is our experimental result again. Here you have the black curve, which is the experimental one. Here you have basically the single electron saddle point, as I showed you before, in blue. So here I changed the color, it's in red, unfortunately. And then I have these, the new curve, the new phase, considering the new saddle point obtained with this model that we try to correct with the random phase approximation phase. And you get the blue curve. And this is, I mean, like, it's really overlapped to the experimental results. So this was why we were saying, okay, so like we succeed in getting some information about the timing of this recombination process. But then we discussed with Misha Ivanov. He pointed us out with our mistake, because I mean, we cannot really, it's not, I mean, our measurement is not perturbative. We have to solve the problem in 2 dimensions, and we have to consider the phase due to the second color component. And if we do so, what we see is that we basically get a new adapted multi-electron saddle point phase that is corrected with the random phase approximation, but I mean, like with the dipole from the random phase approximation, but then it's completely overlapped to the single electron. So it's basically, with this approach, we don't go really farther. So this technique, it's not sensitive to this small change in the recombination time. We cannot see it. It took some time for us to convince ourselves of this. Probably it was kind of, I mean, like, one can actually expect it, because, I mean, the solution must be a saddle point, right? And if you have a very small change of the recombination and ionization time around the saddle, this doesn't really modify the complex phase, and so it cannot really modify the harmonic intensity that much. And this can basically interpret physically in the way that the second harmonic field has no enough time to displace the electron and change the recombination probability. So we are left with our discrepancy. And so it's not a modification of a single trajectory. There may be other trajectory contributing. Maybe this is some kind of interference of different paths that we are looking to. And then we said, okay, now we need to have a contribution from some ab initio theories that may shed light on our measurement. But the configuration is quite challenging from the theoretical point of view, because like we broke the cylindrical symmetry, so there's like the 3-dimensional problem, because we have the second color in perpendicular polarization. And then xenon is a huge atom, we discovered that, so with a lot of electrons, that and you need to include the inner states if you want to look at the role of the 4D orbital. And we discussed with people about these, like we had also a discussion with Armin Strinzi about the possibility for doing that, but at some point, luckily, Stefan Pathe pointed us to Andrew Brown for the Queen's University Belfast, that was able to perform the calculation of our experiment with the R matrix with time dependence. So basically, for me, this is a kind of a black box, but it's solving the semi-relativistic time-dependent Schrödinger equation for general multi-electron atoms and molecules in intense, ultra-short, and arbitrarily polarized laser pulses. I guess this could be, it's probably the title of this paper. And well, so we asked Andrew to perform the calculation in our experimental condition, which is also challenging because we are dealing with mid-IR pulses, long wavelengths, so long excursion time of the electron. And he did perform calculation in 3 conditions. So including only the 5p orbital, including the 5p and 5s orbital, and including the 5p, 5s and 4d orbitals. And now I will show you the results that he got. So with only the 5p orbital, you can see here, this is an harmonic spectrum. And with the experimental parameter that we gave him for performing the calculation for a certain phase, then you can get the cutoff is 71 eV as in the experiment. And then if you do the 2-color scan, this is 4 phases basically here, and the white line is the phase that maximize each photon energy. You can see a behavior which is similar, let's say, to the one that we expect in the single active electron picture. So it rises up to the cutoff and then it changes the shape changes beyond the cutoff, basically. And we don't have signal here above 85 eV because we have exponential decree of the harmonic signal, and then we have a computational noise rising up. So it's like it's only up to 85 eV. Then if we add the 5S, this was really good news for us because something was changing and we were starting to understand something. We see basically a secondary cutoff appearing if we add the 5S orbital. And this is basically could be compatible with direct tunnel ionization from the 5S orbital that we didn't expect at all in our experiment, but I mean, like apparently this is really compatible with our results. And the two scholar can, so this is the spectrum and you have the 2 cutoffs, and then you can see the 2-color scan, and then here you can see a change of the slope beyond the cutoff, which is something that we also see in the experiment. So this was already quite really a good news for us because something was, let's say, we start understanding. It's more complex, which, I mean, but it start to somehow sort out. Then we add the 4D. And what happened is that basically in this way, you basically enable the inelastic scattering and the giant resonance. And in this way, what you have is that you have an increase of the signal around 80, 90, 100 dB. And basically you can see here from the harmonic spectrum, so the full orbital calculation is the yellow one, and you have basically an increase of the signal in this region here, which is associated to the giant resonance. And here you can also see some structures which also are mapped in the phase. Like here you can see the phase delay, still 4 points, and here you can see like that beyond the cutoff in this region here you have several interference patterns appearing basically. So like the giant resonance acts to a boost to make us able to clearly see the signal beyond the cutoff, but also there are these interference that appear. And well, these results are relatively recent, and we worked quite for a long time as well to, let's say, to be able to perform this calculation and to, well, and to compare, like to get in the same experimental, in the same condition as our experiment. And well, now we are in the process that we have these results and we need to compare with our experimental results. So I don't have yet a real conclusion in the sense that it appears that we have 2 basically ionization channels. So we may have ionization from the 5S, but this means that then we have like basically a different family of trajectories we deal with in the recombination. And then we have the inelastic scattering taking place for the recombining electron, both from the one ionized from the 5p and the one ionized from the 5s, and these are affected differently by the giant resonance, by the inelastic scattering. So now, like if you look at the black curve here, which is our phase, the experimental phase, and the white curve here, there is still like something missing. It's like they are not similar. We understood up to some extent, and we are now trying to figure out exactly how much information can be extracted from the comparison of these two results. So in conclusion, basically, I showed you a study of the xenon giant resonance that started back in 2014, and we hope that after 6 years, we will be able to actually give an interpretation of these results. For sure, like the giant resonance enables seeing features that are not possible to see otherwise, and this is such trajectories beyond the cutoff. The harmonic spectroscopy beyond the cutoff is very sensitive to quantum interference, so this could be like a way to do spectroscopy into this region to see tiny quantum interference structure. We failed to adapt the single active electron strong field approximation for grabbing the information about the recombination process, but RMT unveiled the process, unveiled for sure the photoionization process to an extent that we were not expecting before, and probably we will also be able to grab then some information about the recombination. And because of course, like we may be then sensitive to interference between multiple recombination channels in this condition. And I would like to acknowledge, well, this is my group in Milano, and I would like to acknowledge Davide Facciala, because he did all the experimental work and all the strong field approximation calculation for this very long project. And then finally, if I have a minute, I think so, I would like to make an advertisement, since I hope there will be students in the audience. Recently, with also Mark Bracking is involved, we started a Marie Curie innovative training network called SmartX, the study of carrier transporting materials by time-resolved spectroscopy with ultra-short X-ray light. You can see here that we have 15 PhD positions available in a big consortium with many people working both in experiment theory and in industry. And so, I mean, if anybody is interested to apply to this, I mean, just get in contact, because it will be a nice opportunity starting in the autumn. And with this, I thank you for your attention.
Thank you, Caterina, for the excellent talk and amazing results. Now we have time for questions, and I can see that already Manfred Lein is the first to ask. Manfred, do you want to use your microphone?
Yes, can you hear me?
Yes.
Yeah, thanks, Caterina, for the nice talk. Very interesting. I would like to know, I think you did not say anything about the selection of short and long trajectories.
Yes.
I guess you did select them somehow in the experiment. Did you also select them on purpose in the calculation, or was it just using the overall spectrum?
Okay, so, well, I mean, in the experiment, we suppose that we select the short trajectory as usual by the position of the gas jet. Then you can see here this noise here. I mean, like when you go to the cutoff, then there is not clear separation between the two. So we may have interference between the two trajectories, but beyond the cutoff, you should have only one trajectory. In the calculation, I mean, we did the selection in the strong field approximation, while in the, I think I'm not sure about what to say on the RMT calculation. Which...
I can jump in, Caterina, if you want. Sorry, to talk about the RMT calculation. We didn't do any selection. When we tried to do the selection, we introduced a lot of spurious numerical noise, so we just stuck with the overall spectrum for the RMT calculation.
Thank you, Andrew. I wasn't sure. I remember discussing this point, but not sure about the outcome.
Okay, thank you. I think that was my main question. Thank you.
Thank you. And I have another question from the audience. Manfred, sorry, Zdenek Masin. Do you want to ask your question in person?
Hello, can you hear me?
Yes.
Okay, I just want to ask about the possibility that your signal is the result of interference of some other pathways. So actually, it's very well known that the xenon giant resonance actually has two components, which are very wide and overlapping in energy. So have you considered the possibility that your signal is the result of interference of these two recombination pathways?
Yes, I mean, it's like, I think there is also a paper from Stefan pointing out this.
Exactly, yeah.
So we did consider it. The point is that before having Andrew simulation, basically we got convinced that we were not able to look at the recombination. So we didn't expect to have interference in the recombination step with our technique without having another ionization channel. Now we will, because I mean, like what you can see from the experimental data is that you have two slope changes. And at the very beginning we thought, okay, then these two slope changes are associated to the two different processes. It will be very nice. That was my, let's say, hope at the very beginning. That was few years after 2014, but still few years since now. But then, like, turned out okay. Like in the development, it was, we cannot really see that. Now we got back to the possibility that we are seeing something because we have basically the time to affect the trajectories due to the different ionization channel. And so then we will get back to consider this possibility. That should be, I mean, included in this also. Andrew, you can jump in if it's wrong, but I think it should be considered in the full calculation, including all for the shell. So yeah, that would be cool.
Thank you. Thank you.
Thank you, Caterina.